Organizations dedicate massive amounts of capital and engineering power to construct heavily fortified network perimeters. The goal is to filter incoming traffic and drop anything that looks like a threat before it reaches the internal infrastructure. The problem with this approach is that to conduct business on the web, a company has to let customers in. Firewalls are required to leave ports 80 and 443 wide open to allow standard HTTP and HTTPS traffic to pass through. An attacker simply formats their attack as a structurally legitimate HTTP GET request. The perimeter defenses inspect the packet, see that it conforms to web standards, and waves it right through. It travels unhindered until the payload detonates directly within the application server's code. This highlights the core premise of the DevSecOps code auditor. The actual undefended attack surface is not the outer network wall, it is the application logic itself, and specifically how that application validates incoming data. Treating security strictly as a network infrastructure problem guarantees application layer compromise by malicious inputs. To map exactly how these malicious inputs are weaponized, we have to look at the environment from the developer's perspective, using a standard enterprise e-commerce platform as our baseline architecture. Unlike legacy web servers that deliver static HTML documents, this platform relies on dynamic web pages. The server executes code to generate content on the fly, based on who is logging in, what they are buying, and the time of day. The first parameters of execution happen right in the user's browser. When a standard user fills out a web form, client-side scripts, usually written in JavaScript, perform the initial processing of that input. Once the user clicks Submit, the browser packages that input and executes the handoff, sending the data across the network and into the server-side environment. Historically, this raw data movement was handled by the Common Gateway Interface, or CGI. CGI is the standard that determines exactly how the web server routes that incoming information to the application logic. Every dynamic transition point between the client browser, the CGI routing, and the server logic requires the passing of data. Every one of those handoffs introduces a vector for untrusted input injection. On the server side, developers choose specific frameworks. On the left is the Microsoft IAST stack, utilizing languages like classic ASP, Cold Fusion, or modern ASP.NET. On the right is the open source alternative, featuring an Apache web server daemon processing PHP scripts. Regardless of the stack, developers rarely build enterprise applications entirely from scratch. They rely heavily on third-party frameworks and imported libraries to accelerate complex deployments. From the auditor's perspective, this creates an immediate risk. These imported libraries function as unverified black boxes operating deep within the custom code. Relying on unpatched third-party code introduces hidden supply chain vulnerabilities. A flaw discovered in an obscure dependency leaves the application exposed until a patch is issued. Importing an external framework equates to importing its entire historical vulnerability footprint into the application perimeter. Once the server processes the logic, it has to store or retrieve data. It uses the database connectivity layer, a bridge translating web application logic into relational database commands. These connections have evolved from standard Open Database Connectivity, or ODBC methods, into optimized protocols like Microsoft's OLEDB connection strings. To understand the vulnerability, let's trace an ActiveX data object connection. First, the application creates the connection parameter and actively opens the database link. Then, it creates a record set, queries specific variables, and finally, closes the record set and connection. This specific transport layer is the primary locus of catastrophic failure. It is exactly here that untrusted user input from a web form is compiled into raw SQL commands. If the application fails to explicitly sanitize incoming web form inputs, the database connector acts as a direct conduit for exploitation. The Open Web Application Security Project, or OWASP, tracks the most critical web risks in their top 10 framework. They consistently list injection flaws as the primary method used to dismantle these data connectors. This is OWASP WebGoat, a sandbox environment for safely demonstrating exploits. An auditor tests for SQL injection by deliberately injecting punctuation marks, like a single quotation mark, into an input field to break the query syntax and generate a database error. If the developers leave debugging mode enabled, the application will not hide the failure. It will leak verbose database schema details directly back to the attacker through those error messages. The attacker injects a SQL payload into a login form. Select asterisk from customer where TBL username equals / equals or 1 equals 1. The or 1 equals 1 creates a universally true condition. Appending double hyphens comments out the password requirement entirely, tricking the backend database. By manipulating the logic, SQL injection transforms the database connector from a legitimate data retrieval tool into a remote code execution weapon. Security assessments extend beyond raw code injection. Auditors also conduct business logic testing, focusing on subverting operational procedures rather than breaking syntax. For example, an attacker utilizes creative logic bypasses to force a banking application to execute a wire transfer, even when the originating account does not maintain an adequate balance. This exploit succeeds because the application relies on insufficient client-side controls. If those checks are not paired with corresponding unbypassable server-side validation, the logic fails. Cryptographic misconfigurations present another major vulnerability. Utilizing a known weak encryption method is a critical error, but it is only a fraction of the problem. Developers might design an application that doesn't strictly enforce secure channels. Employing bad random number generators or relying on self-signed certificates instead of purchased ones completely compromises the secure channel's integrity. Perfectly sanitized code is highly vulnerable if the underlying business logic or the cryptographic handshakes are deeply flawed. Organizations require a triad of continuous assessments. First is SAST, white box auditing of uncompiled source code. Second is DAST, analyzing the running application from an external attacker's perspective. Third is IAST, using an internal agent to monitor runtime behavior. Auditors augment these methodologies with automated black box scanners, like Wapiti. These tools blindly fuzz web inputs, rapidly injecting data at scale to see what the application will accept. The most critical operational tools for testing are intercepting proxies. This split screen shows Burp Suite Community Edition intercepting an HTTP GET request. Testers use proxies to actively pause the connection, inspect parameters, tamper with requests, and alter cookies mid-transit. Secure code architecture, paired with active, continuous proxy manipulation, is the only true defense against modern application layer compromise.